All right, let's pick it up where we left off. We've got a bunch of points in some dimensional space, 2 because it's easy for us to visualize. These points are represented with respect to the canonical basis, perfectly fine basis, but we are going to seek a new orthonormal basis that allows us to reduce the dimensionality of this data so we can both visualize it and be more computationally efficient when we're manipulating this data in our favorite machine learning algorithms. What we talked about in the last segment is computing the covariance matrix. So let me just remind you what that is. We have our data matrix that has the x coordinates and the y coordinates along the rows. If this was 3-dimensional data, I'd have the z along the next row. And I'm going to compute the covariance matrix as the product of the data matrix and the data matrix transpose. That creates a little 2 by 2. This is 2 by n. This is n by 2. On the diagonal is the variance of the data in each of the individual dimensions. And in the off diagonal is the covariance of the data. How much does one value tell me about the other value? And the reason why the covariance is useful here is that we want to diagonalize the covariance matrix so there is that dependence is gone, and that is the equivalent of reducing dimensionality. So what we're going to do is create a new representation, let me call that d hat, which is simply multiplying the data, d, by a new basis, which is just 2 by 2. Why 2 by 2? What's my initial basis? 1, 0, 0, 1. And remember that the way we compute the new representation for an orthonormal transform basis is to simply put the basis vectors on the rows and compute a dot product with the data. So the new representation is nothing more than that. But of course, this is still 2-dimensional. We'll get to that in a little bit. We're going to start throwing some information away in a little bit to do the dimensionality reduction. And so now the question is, what is B? B, of course, is going to depend on C, which is the covariance matrix. And in particular, I'm not actually going to prove this, although the proof is relatively elegant, but it takes a little bit longer than we have time for here. But if the rows of B are the eigenvectors, there they are again. Eigenvectors are so incredibly important, even though when you learned them in linear algebra, it didn't seem that way. If the rows of B are the eigenvectors of the covariance matrix, C, then the covariance matrix of the transformed data, which is d hat here, is diagonal. And this is actually relatively easy to prove, but I don't want to get into too much of that proof here. So what I mean by that is if I compute the covariance matrix of d hat, the transformed data, then this matrix is, as desired, diagonal, which means I've eliminated the covariance of the data, and now I can start to do dimensionality reduction. Let me just remind you, I think you probably know this, that the eigenvector of a square matrix C simply satisfies this equation here. That is E, C times E is simply a scaled version of E. Now, what I've done here doesn't seem like I've done dimensionality reduction, because all I've done is I've taken a 2 by 2 matrix, I've computed 2 eigenvectors, I've packed those eigenvectors into the rows of that matrix B, and now I've gone from a 2-dimensional representation to a 2-dimensional representation. How is this any better? Well, I have actually done something, because this covariance matrix is diagonal, which means the representation is different. And it's going to turn out that the eigenvalues here are going to be what we use to determine which of the dimensions in this new representation we can throw away. And we'll take a look at that when we come back, along with some code and then some application to images.